Hi, this is the review for the first test in Organic 2 for the fall of 2025. And so I'll be going through the practice test. People will be here with me to kind of go through it. And if you guys have any questions, feel free to stop me, speak up, or I might throw some questions out to you guys just to give a little bit of time to think about something. So if you guys wouldn't mind speaking up if you know the answer to something, and we can kind of move on from there. Um, I'm not going to spend too much time talking about these things. Uh, the these are things you could just look up for the most part. So these are kind of the conceptual things. So uh, you can expect to see questions. Any number of these kind of questions, calculating equivalent protons would probably be the hardest out of all of these. The rest of them are pretty straightforward answers. So explain kind of, what we use NMRs for, how they work in general, just kind of what kind of waves are used, why do we use a magnet, what are we exciting, what are we looking at, OH and NH2 peaks, these are exchangeable protons. Why are they exchangeable? Why does that affect how they react with other things? These are more likely than not going to be either short answer or multiple choice questions that you can kind of just get through and answer relatively quickly. Um, these questions are simple arrow pushing questions. So all I'm trying to ask you with these is if I give you the arrows, can you tell me what the product is? Or if I give you the product, can you tell me what the arrows are? Sorry, it got pixelated. Um, so this is just an interpreting arrows question. Whenever I see something like this, I'd be tempted to just draw the starting materials over again and then change them as I interpret the arrows. So I have this going on, and I've got a positive charge, and I've got a bromine that has a lone pair in electrons. So what's realistically happening here is that bromine is forming a bond with this hydrogen. So I'm going to go ahead and change that. So I've got HBr, and that bromine is no longer negatively charged. That hydrogen is no longer attached to this carbon, and those electrons went to this bond, which means that this carbon gained electrons and is no longer positively charged. So that would give me the answer here. This one's a little bit trickier. So this one requires you to see, okay, I'm going to, just like always, I'm going to redraw my starting materials and kind of see from there what's happening. Well, the easiest arrow to interpret, in my opinion, is this bond breaking off and going to this bromine. So those electrons end up on the bromine, which means it gained electrons. I'm going to give it a negative charge. Meanwhile, this double bond broke off and it formed a bond with the bromine. Meanwhile, this bromine formed a bond with this carbon. So notice something, if I keep track of the electrons, this carbon was part of a double bond and it stayed a part of a bond to the bromine. This bromine gained a bond. It gained two bonds and it lost a bond. So this bromine is actually positively charged. Or sorry, it lost two bonds, lost two electrons, two sets of electrons, and it gained a bond. So it's positively charged. I want to make sure that I always kind of maintain a net charge that's the same, right? There should be a conservation of charge. Everything is neutral in this, so all of the charges should add up to be neutral here. Make sure that you can explain every arrow. Like this bromine going here, there needs to be a bond between bromine and this carbon, non-negotiable. This double bond is a little bit trickier to interpret, but because I already have four bonds on this carbon from this bromine, I have to add the bond to the other carbon. This one's just a simple substitution. OH is adding directly into that carbon. I need to explain that oxygen forming a bond with that carbon. We have a few more, but I'm going to kind of skip around. So This one, again, every time I see a metal, I want to draw out the ionic. It informs me kind of where I'm going. It gives me um, evidence about what's going on. This one's kind of tricky. So what I would be looking at here is what changes. So a lot of people might be tempted to say, this is going down here. That's a very common wrong answer with a question like this. The problem with this is that there's already four bonds on that carbon. That carbon can't hold extra electrons without getting rid of something. Notice something else. This becomes negatively charged. So somehow it gains electrons, somehow it loses protons. So that's the evidence I would need to start saying, okay, something else is changing here. I go from two hydrogens on this carbon to one hydrogen on this carbon. That's a big tell. All right. So it's one common mistake people make when it comes to arrow pushing is that they always just want to explain the movement of bonds around. But if atoms are missing or present, that has to be explained as well. And honestly, it's the bigger factor. So I would notice, hey, there's a double bond here that there wasn't here. That means there's actually one less proton. So drawing in the implied lone pairs and protons around the things that change can be helpful if you get stuck. So I have to take a proton. The only thing that could take a proton is this OH, since electrons take protons. And since that proton's no longer attached, I need this bond to go somewhere. And so I'm going to put it here. Since this carbon already has four bonds, I'm going to push it up. Um, this is the same thing in reverse, and this was my bad. This needs to be some sort of acid. So that won't work. So that was my fault. That was a typo in the practice set. So just try this on your own with an acid, and hopefully it'll make a little bit more sense. Again, it's basically the same thing, but backwards. All right, again, um, I noticed that this gains electrons somehow. I go from a positive charge to neutral. But really, what stands out to me is that there's three hydrogens on this carbon, and there's only two here. That's a big tell that there's something going on. This is an elimination reaction. I see a metal, I'm going to draw my charges out every single time. And the only way I can explain this is to take a hydrogen. What's tricky about these is a lot of people's first instinct is just to put the negative charge directly into the positive charge. But that's not what we see in practice. We can satisfy that positive charge in a bunch of different ways. And in this case, what we're doing is the elimination. Um, you might get to this question and say, I don't know what OTS is. It doesn't really matter. We have to explain something. And what I see is we have to explain the formation of the product. We're given the product. So what that is doesn't really matter. We know that somehow this OET needs to become this OET. So that tells me that this is a leaving group. It has to be because it's gone in the final product. So what I have to do is I have to explain somehow this garnet oxygen binding to this carbon, this garnet oxygen binding to this carbon. So I'm going to show an arrow that shows the formation of that. And since that leaving group is no longer there, I have to kick it off. One thing to note, oftentimes I see this, and you will lose points on this test. If you draw this arrow from here, it is wrong. There are no electrons, there are no lone pairs on that carbon. The electrons are in this bond. It needs to come very specifically from that bond. If it comes from that carbon, it is wrong. So be very specific about your arrows. Be very precise. Otherwise, you risk being wrong. This one is, again, I see metals. I'm going to draw out my charges. And all I'm doing is I'm noticing that this hydrogen is one of these two hydrogens. So it needs to use its lone pairs to take that hydrogen. But that hydrogen is no longer attached. So this bond needs to go to the nitrogen to make it no longer be positive charge. Just a deprotonation mechanism. All right, then we have this one where um, this bond is leaving, and it seems clear that those electrons are staying with this carbon, right? Because this MgBr ends up with a positive charge. It loses out on electrons. So these electrons are going to the carbon. So worst case scenario, I'm going to balance this, right? I'm going to say, what am I missing? Well, there's 2 carbons here, and there's 1, 2, 3. I'm going to go ahead and number that out. So I've got 1, 2, 1, 2, 3, and then I've got 4, 5. What is 4 binding to?
Two.
Carbon.
It has to be bound to carbon 2, right? Because that's where the arrow ends. Very specifically has to be bound to that carbon. Otherwise, the arrow would go somewhere else. This bond means the oxygen is no longer connected to 2, which makes sense because then 2 would have too many bonds. But it's still connected to 3. So it's still connected to 3, but now its gained electrons has a negative charge. And this one's something that I hope you guys have seen before. I'm going to draw the starting materials again. And this time, this double bond broke to make that OH. This nitrogen very specifically bound to this carbon. And then it has a hydrogen and 2 methyls on it. None of those changed. Now, what people will lose points on a question like this, what really this question is trying to get at is, can you balance these charges? Can you see that this OH has gained electrons and that this nitrogen has lost electrons? So this nitrogen now has a positive charge. If you don't put the charge, you will lose points. The charge is important. All right. That's arrow pushing. That's kind of the heart of what we do. We haven't really been tested on it that much, so I'm going to put it on this test. I'm going to put questions that look like this. I'm going to put eliminations, substitutions, things with metals in them. I'm going to put things with charges just to see if you guys can follow the general flow of electrons, can follow the charges, can understand what those errors are communicating. Okay, so one thing I want to note about this question, on the test, I'm not going to include this, which kind of makes everything else make more sense. So I'm sorry. There were some questions on here that you can't balance the charge of and don't actually have tetrahedral intermediates. So on the test, that is not going to be included. It's just going to be, can you do the first 2 steps? Can you tell me that this is the nucleophile because it's an amine, this is the electrophile, this is the acid? Can you tell me that the first step of the mechanism is the electrophile? And in this case, the electrophile is a carbonyl, which means that it's with a carbonyl. If I have a carbonyl and an acid, it's always going to be the oxygen on the carbonyl that takes the proton. And I end up here every single time. It's always going to be the oxygen of the carbonyl taking the proton from the acid. Then step 2 is nucleophile attacking electrophile. And that's all I need. That's all I need from this. Make sure you're balancing the charge. So step 1, acid protonates electrophile, base deprotonates nucleophile, and then 2, nucleophile attack electrophile. That's all I want. I want to see how well you guys can do these first 2 steps. All right. Here, I know that sodium hydride's a base because I know that sodium is a metal. That means hydrogen has to have the negative charge. If I see a metal in something, it's probably basic or nucleophilic. This looks like my nucleophile. It's an alcohol, pretty straight up nucleophile. And then this one's a little tricky. This is a throwback to organic one, but we put it in the chart every day. Every time I see OTS, OTF, that tells me I've got a bulky oxygen. This, again, is a leaving group. So what do I do when I have a nucleophile-electrophile? That means that, sorry, this is my electrophile. So step one, base deprotonase nucleophile. So I'm going to take the electrons from my base. I'm going to take the hydrogen from the nucleophile. That ends up here. Step two is nucleophile attack electrophilic carbon and kick off leaving group, and I end up here. Now, what's tricky about this one is that it's in a ring, or that I've got a nucleophile that's here, and my electrophile is on the same molecule. So if something attacks itself, that forms a ring, right? It's like me grabbing my own ankle. I form a ring between my arm and my leg. So KOTBU, I see a metal. This is on the chart. This is a common base. So this is a base. Step one, base deprotonates nucleophile. So step one, my base is going to take a proton from my nucleophile. That gives a negative charge to my nucleophile. Step two is nucleophile, attack electrophile, and push up. So this is where it gets tricky. I know I'm going to form a ring because my molecule attacks itself. So I'm going to number the carbons, 2, 3, 4, 5. The oxygen is going to be part of the ring. So the oxygen is here. 5 is bound to 1, 2, 3, 4. It's a 5-membered ring with an oxygen in it. 1 has here and has a negative charge.
Excuse me. Isn't that a bulky base?
It is a bulky base.
Wouldn't it like make elimination for, I mean, wouldn't it make like a double bond at the end? Or it doesn't
What do you mean? Where?
at the end of the chain?
So you're saying why doesn't this just eliminate this OH?
Yeah.
So yeah, okay. If I had KOTBU with something that had a leaving group on it, I could do an elimination. Right? That's something that happens all the time.
Oh,
But
got it.
why does that not apply here? What am I doing for this elimination? What is it taking?
A proton.
It's taking a proton from this carbon,
Yeah.
which typically carbons don't want to give up protons very easily. So if it can take a much more acidic OH proton, it will. Right? Plus OH isn't a very good leaving group. So it does this in this case. So in order to do the elimination, you would need a leaving group, which we don't have. OH by itself isn't a great leaving group. That's why if we want it to leave, we typically have to protonate it. But in
Got it.
basic settings, we're going to deprotonate it.
Thank you.
That's a good question. But yeah, it has to do with the leaving group, OH not being a leaving group, it taking this proton instead of the carbon proton. It's a great question. All right. This is my nucleophile. This is my electrophile. Again, I mean, I'm not going to give you any acid bases that you really haven't seen before. So recognize that sodium hydride's on the list of things to know, and it's a base. So step one is base deprotonates nucleophile. So I'm going to take the proton from the nucleophile, give it the electrons from that bond. Step two, nucleophile, attack electrophile. That's all you need to show. I would also know whether or not something is a tetrahedral intermediate. So if it adds into a carbonyl, that is a tetrahedral intermediate, right? This is a TI. This is not a TI. Why?
It didn't add into a
It
carbonyl.
didn't add into a carbonyl, right? So tetrahedral intermediates only happen like this is a TI. This is a tetrahedral intermediate because I added into a carbonyl. This is a tetrahedral intermediate because I added in a carbonyl. Nucleophile, electrophile. Oh, sorry. Skipping a step. I see H2SO4. I'm just going to write HA out, right? That just means acid. Step one is electrophile gets protonated by acid. Um, feel free to write R to kind of shorthand some things for all of the steps except for the final step. So on the final step, don't write R, but here I could write R just to mean everything past that point to save myself time. Step two is nucleophile attack electrophile, and we end up here. Oh, sorry. Forgot something. All right. And don't forget your charge. So can you recognize nucleophiles, electrophiles? Can you do acid base to activate either the nucleophile or electrophile? Can you understand when you form a tetrahedral intermediate versus when you don't form a tetrahedral intermediate? Can you recognize what a leaving group looks like? Can you either form or break a ring? Those are all important skills that I'm going to be testing using these kind of questions. Now this is, once we form the tetrahedral intermediate, how do we proceed? So on the test, I can't make things red because it goes black and white. So it's going to be bolded like it was on the quiz. I'll try to make it a little bit more obvious than it was on the quiz so you guys don't get too thrown off here. But essentially all this is asking is, from this point on, can you finish the mechanism? Once we get to the tetrahedral intermediate, can you finish this? So this is the red is what's just added, so it cannot be the leaving group. So the next best leaving group would be here. Has to be my leaving group. This would be my kicking group. I'm not going to circle that. I'm just going to say kicking group because it's the only thing with lone pairs. My leaving group already has the extra proton, so I don't have to do anything else. I can just collapse and kick, which is the step that forms this here. And I won't give you one on the test. This is my fault. I didn't think this through enough when I made this question. I won't give you on the test things that end with a positive charge that you can't neutralize. This is a real tetrahedral intermediate that you will see, or a real like thing you'll see, but you'll have a different way to neutralize this in the future. But right now, that's all I wanted you to do.
For the top one, or the one you just did, I thought we were allowed to assume that there was always water if it's acidic starting conditions.
Well, water, if you added water, it'll just bring us back here. Which I mean isn't wrong.
Okay.
Yeah, but don't worry about it. in reality, what's going to happen here is I would actually add a second equivalent of this, and we'd keep going, which you've actually seen before. But so these probably weren't the best worded versions of these questions. I made another tetrahedral intermediate worksheet that I posted, and I'll put the answers up to those later. That give a little bit tougher problems for this section and give kind of, probably better questions for these tetrahedral intermediate things. This is a new question type that I'm trying out. And so I'm still kind of learning how to write questions that work. This one, what I'd expect you to see is like, hey, there's no leaving group here. So that's all we can do. There's no leaving group. We'll stick here. This next one, this is a good kicking group. This is my best leaving group. I don't have an extra proton around. I'm not in an acidic environment. There's no positive charge. So that's all I can do. So I'm just going to go ahead and kick off this OH, and I end up here. In this case, this is my best leaving group because this group was just added. This is my best kicking group. But the trick of this one is that I need to get this extra proton, this extra positive charge onto my leaving group to make it better. So I'm going to use water in acidic conditions to take this proton. Then, now that that water has taken the proton, I can have my leaving group take that proton, and I am here. Now I've activated my leaving group. I've made it as good as it can be, and I can do the kick, collapse and kick step. So I'm going to get here. And again, there's not a great way to neutralize that. And so I'm sorry, wasn't the best question I could have asked. But that's all I'd be looking for here. And on the test, I will not give you one that ends in a positive charge. I just want to see, can you recognize what a leaving group and a kicking group is? Can you show me a collapse and kick? In acidic conditions, can you transfer the proton to the leaving group? Those are the three things I'm looking for here. And it is totally also fair game for you to say that there is no leaving group here. That is another way I could ask this question. So let me write that down. What I care about is, can you recognize leaving group and kicking group? Can you collapse and kick? And can you transfer proton in acidic conditions? That's all I'm looking for here. This is what I want. So a lot of you guys, what, sorry?
Acidic conditions refers to like specifically if the tetrahedral intermediate starts positive
Yes.
or starts with a positive charge.
Yes.
Okay.
So notice something. Let's go back up here. There's an acid here. When we get to the tetrahedral intermediate, there's a positive charge. There's a base here. When we get to the tetrahedral intermediate, there's a negative charge. There's a base here. When we get to the tetrahedral intermediate, there's a negative charge. There's no tetrahedral intermediate for this one. There's an acid here. When we get to the tetrahedral intermediate, there's a positive charge. So that's just a trend. That's always there. So yes, acidic conditions. Means that there's a plus charge around. There's an extra proton that can be transferred from one place to the other. Notice here, like I don't have an extra proton to move anywhere. I can't, there's nothing that could give that leaving group an extra proton without making something else negative, or like there's nothing to do here. Okay. Likewise here, my best leaving group has to be this OH, seeing as what was just added, the red thing cannot be a leaving group. My best kicking group is this, so I have to use water to take the proton from my kicking group.
Why wouldn't the NH be a better leaving group?
That's a good question. So leaving group. Leaving groups, the best leaving groups are going to be OR to OH to NR 2 to NH2. And then halogens will be the best leaving groups. So that's leaving groups, and then kicking groups, we favor OHs, OR, NH2s to NR.
For kicking groups, would a negatively charged oxygen be the best?
Yeah, I mean, it would be.
But in that question, there's an OH, so we wouldn't favor that OH to kick.
No, choose the leaving group first.
Okay.
Yeah, that's a good question. My eye first goes to the leaving group. So I've now got to give the proton to the other oxygen here. Those were good questions, by the way. Keep them coming. Now I've turned that into a good leaving group. And now my OH can collapse and kick. And again, I gave you another one that we can't satisfy the positive charge of. So that's my bad. I will not give that on a test. But if you got here, be happy. You're doing it right. All right. So with these carbon NMR matching questions, I would make a line right here and say this is sp3 and sp, and this is sp2. So I mean, the simplest thing to do to answer this question would be, I only have one sp3 carbon. This, because of symmetry, would have only one peak. This one would have 4 different carbon peaks, sp3 carbon peaks. Again, likewise, this one would have 4 because there's no symmetry through either one of these. So every sp3 carbon would be its own peak. And this one would have 2. So it has to be this guy. Right. So this is just a different way to say, hey, do you understand symmetry? Do you understand what an sp3 carbon is? Do you understand kind of this arbitrary division point on a carbon NMR that can help us kind of differentiate these molecules? It's not really that helpful for building up a molecule, making a molecule from scratch, but it can be very helpful for just kind of verifying you have what you think you have, right? So this is kind of the context at which we usually use carbon NMR. Do we have as many equivalent carbons as we expect? Okay. So 2 more question types. So this is a synthesis. We're going to need multiple reactions to get this final product. So this is exactly what we did on Monday. I would look at this final product and say, how did I get here? Right? How did I get from point A to point B? So I would say I'm going to work backwards and I'm going to choose. I know that this had to be done using an alcohol and a thing with a leaving group. And my thing with a leaving group had to be on this carbon. Right? I'm choosing the leaving group to be on this side because that gives me a primary leaving group versus secondary leaving group, which is more likely to do SN2. So now I need to somehow turn this into 1. So I've got to move this heteroatom a carbon over. So I've got to use a base to eliminate. And then I can use H3O plus to move it over. And then same thing here. So this one's actually kind of trickier than I meant for it to be. So if you did H2SO4 in heat, I'm not gonna be too upset about that. H2SO4 in heat would actually make them more substituted double bond. So it'd put the double bond on this side, which is not what we want. So I'm gonna do it the old-fashioned way and turn this OH into a leaving group. That way I can use a bulky base and give this one. This is the most technically correct answer. So this gives me a double bond that's touching the carbon I want that bromine to be on. So now I can do HBr, H2O2 to put this bromine here. All right. So I think a lot of this is not too bad. I'm not going to spend time doing the rest of them. The rest of them are very similar, but you know, you just change kind of what the starting materials are. So I'm going to post the answers to the rest of them, but I won't spend the rest of the time talking about them because they're just very similar. Decide what your final products need to look like in order to get the final product, then work your way through the starting materials to try to make them, right? So this is 1 and this is 2. Do you guys have questions about synthesis before I move on? Nope. Synthesis tends to be okay. You guys tend to do okay in synthesis. I think this is where people this is the tough part. 2 times, first thing I'm going to do is degrees of unsaturation plus 2 minus 10 all over 2. That's 12 minus 10 is 2, so I have 1 degree of unsaturation. I'm going to kind of disregard the mass spec and carbon NMR. That they're not going to tell me that much. They're not really useful to my time. I can note that I have an OH and a carbonyl. That's useful information. So that's 2, at least 2 of my 3. I could have multiple OHs or multiple carbonyls. That's also a possibility. But we'll keep building the molecule. All right. So this is a broad peak. So that tells me I have an OH. That's my OH. It's not going to split anything. So I'm going to note that. I don't have any benzene, which wouldn't make any sense anyway because I only have 1 degree of unsaturation. So I'm going to start with my multiple of 3. So this will be my black carbon. That is a carbon of 3, and it has 2 neighbors. So that has to be my first fragment. So I've checked this guy off. And can I find this garnet carbon anywhere? Well, it can't be this, 3 hydrogens. It has to be this. So this is my garnet. And it's a quartet. So I would expect to have 3 neighbors. So this is done. I've checked off 2 of my, I've actually checked off 3 of my Proton NMR peaks. Now I've got to move on to the last 2. I'll do this one in blue. CH, this is my blue one, and it has 1 neighbor. And that 1 neighbor, which has to be this one, right? That's the only thing that integrates to 1. It has 1, 2, 3 neighbors. So that's checked off too, and there's 2 things that have no protons on them. So check, check. So I already have built something up, right? I have an OH that I know I have somewhere. I have a carbonyl that I know I have somewhere. And so now I'm going to, now I'm stuck. So I've got to go back and I've got to make sure that I've accounted for everything on my Proton NMR. I've got to make sure I've accounted for everything in my chemical formula. So I have 1, 2, 3, 4, 5 carbons. So that's all the carbons I would expect. No more carbons. 10 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I'm counting a R as a hydrogen. That's my bad. All right. I was like, how does that math? Okay. Yes, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the OH is 10, right? That matches up with my chemical formula. So the only thing I'm missing is 1 oxygen. So I can't have 1 oxygen that's part of a carbonyl, and I don't have another OH. So this oxygen, there are only 3 ways oxygens can come, and we have them in all 3 ways here. They can either be an ether, an alcohol, or a carbonyl. Okay. So I like to think, when I start piecing things together, I like to think in terms of this is an end piece. I know this is an end piece because there's only 1 R group on it. That makes this OH, this is an end piece. So I have 2 end pieces and 3 pieces with 2 R's in them that are my middle pieces. So now is kind of the tricky part. Now is the part where this is how you get the 100%. This is how you, if you're able to just kind of throw these together into a molecule, you'll probably at least get 7 or 8 out of 10 points, even if you're wrong. But this is where we can start using shift and thoughts like that to kind of start informing our guess. So this 2 hydrogen, this 1 hydrogen, they're both past 3. So I'd expect them both to be near an OH. Or sorry, near an oxygen. So that means that so I would look at this. This is a 2 hydrogen quartet. This is this, and I know it's got to be next to an oxygen because it's past 3. But it can't be next to this OH because that would be the end of the molecule. If I put the 2 end pieces together, it'd be done. So that can't be the oxygen it's next to. It's not next to a carbon of a carbonyl, otherwise it wouldn't be down by 4. So this has to be next to this ether. That is the only oxygen I can have that doesn't end my chain. So I've combined those two chunks. So now the only way that I also know that this carbon has to be next to an oxygen. And the only way it can be directly attached to an oxygen is if one of these R groups is the OH, because that's all I have left. And now I have two end pieces, right? Now this only has one R group and this is one group. I have two end pieces with one middle piece. So there's only one way to put that together from here. So it would look like this: carbonyl with an oxygen and an ethyl group on one side, and a carbon with an OH, one, and another carbon on this side. So this has to be my molecule. Where have you guys gotten stuck on this one? What did I do that was tricky?
I made like a completely different, like I have all the components and I just put them together really differently, but I somehow like still got the same integration. So I guess I just got the shifting.
Yep. So that's really where shift comes in, that last bit, to say, okay, these both have to be next to an oxygen and one can only be connected in a certain way, right? Because if I put the alcohol on this one, then it closes off the whole chain and that can't work, right? There's a little bit of guess and check involved in there. So that has to be the ether. That's kind of how I think about this. But this is a tricky question, but it's a good question.
I have a question. I'm still a little confused on the placement of the carbonyl versus the ether. I
Mhm.
put the ether next to the OH with the OH connected to a carbon at the end. So
Ether next to the OH.
yeah.
So was it like this? I mean,
No. The OH would be on attached to the carbon that's connected to the ether.
this one.
Like that.
So you flipped the ester.
Yeah.
So the reason why I say it's not this is because
Mm.
this hydrogen would be right next to two oxygens. I would expect it to be way more downfield than this one. This I would expect a shift of like 2 because it's not directly connected to an oxygen over here. Where this one I would expect almost to be like 5 or 6 because it's connected to two oxygens. So
Okay.
that's where shifting comes into play. Seeing these shifts being so similar tells me that this is more reasonable than this is. They both have to be next to, being on this side of an ester means that I'm somewhere around 2, where being on this side of an ester directly attached to the oxygen means I'm closer to 4 or even
Okay.
above 4. So that's where you have to take, that's the difference between like an 8 or 9 and a 10 is, can you understand, can you then use shift to place these components in the right spot?
Okay, thank you.
All right. So I've got C 2 times 8 plus 2 minus 9 minus 1. Chlorine's minus 1 divided by 2. So that's 16. 18 minus 10 is 8 divided by 2. That's 4. So my first thought is benzene. I'm going to ignore these and come here. There's no OH or carbonyl, which isn't surprising because I don't even have an oxygen in here. So I probably do have a benzene. I have peaks around 7. And I have a tri-substituted benzene. I have 3 things on my benzene. So get a benzene with only 3 hydrogens on it and 3 R groups. So there's really only so many ways you can do a tri-substitute benzene. But I have some symmetry because that's a 2 hydrogen peak versus a 1 hydrogen peak. I have 6 hydrogens here, which also tells me that I have symmetry. So these are probably 2 methyls, and they're symmetrical to each other. I also have a chlorine. So the only way that I could have symmetry on a benzene ring with 3 things on it would be to have 2 methyls here and 1 chlorine here, right? That gives me symmetry right down the middle. That's the only way to have symmetry with 3 things on it. I can't really orient it anyway else. It also would explain why this 2 hydrogen and this 2 hydrogen are equivalent. This one's by itself. So this one is one of the ones that the fragments aren't hard. You have benzene. You probably have 2 methyls that are equivalent. They can't be an isopropyl because it's not a doublet. And then you have the chlorine, and really it's the only way you could put it together.
I have a question on that one.
Yes.
So I put it to where the chlorine in between the 2 methyls because of the splitting of the hydrogens.
Oh, that's actually a good
Like-
point. That's probably right, actually. Hold on. You're right. Hold on. Let's think about that.
Oh,
Yeah, there
fine.
are 2 different ways you could do that. Look at me. I told you I wouldn't get a perfect score on this class. Yeah, the splitting. Yeah, this is a triplet and this is a doublet. So if I look at this one, I would expect 2 different singlets, which is not what I get. So yeah, you're totally right. That is not the right answer. Thanks. All right, this would be my triplet because it would have 2 neighbors. Good point. Yeah. So yeah, there's some tricks to Proton NMR, but if you do enough of these practice problems, you'll see the trends. And little things like messing up the ester or even benzene substitution will take away a couple. Like I probably would have gotten 8 points on that question if I had put what I originally thought. But yeah, so just make sure that you've got your fragments, you've got the big idea of like, what are the different ways these carbons are connected to each other, what are the different hydrogens, and then start piecing them together using the best logic you can with the splitting and integration and shift that you have. All right. So that's the whole practice test. There's a bunch more practice just littered throughout the course that you could go back and try. I would suggest like if there's particular things that you have issues with, like say you did this and none of your tetrahedral intermediates looked right and you kept getting the wrong one, I'd go back to that worksheet and get a fresh copy and try it again. If you didn't know what you were looking at with carbon NMR, I mean, we didn't really do that much practice with it. Synthesis, I would go back and start with the synthesis practice problems that we did in class because they're a little bit easier and they'll get you here. I mean, I'm not going to make these too challenging. I just want you guys to get used to the kind of process that is synthesis before we start throwing more reactions on it. Do you guys have any other questions?
For the synthesis ones you put on the practice test, are those going to be like the highest level of difficulty?
These are actually taken straight from the test last year.
Okay.
These are the 3 different versions of the test. So, yeah, I might could change these up a little bit, put a benzene somewhere or whatever, but the aspects of it are the same. Are going to be the same. Can you eliminate? Can you move something? Can you do a substitution? Really, can you show me that you remember the important bits from Orgo 1, eliminations, additions, substitutions, and then use them in a practical way? That's the point here. So yeah, that's the focus isn't the synthesis, the focus is the Proton NMR. and really getting arrow pushing down. But if you guys, but I do want to see, like, can you get the, you know, the motions down of what makes a synthesis a synthesis. And yeah. Any other questions? Those were good. No? I just got nervous that I wasn't recording. That would have been bad. All right. Well, thank you guys for stopping by. I appreciate all 21 of you that are still here. So I'll see you guys tomorrow ready with the test. Good luck, y'all.